Welcome back. So last time we ended by defining the potential, the electric potential, as being an integral of the electric field along some path or along some parameterization. But we left the left-hand side of the potential as the change in potential because we wanted to remember that the potential is defined from one point to another in my space. Well, at the end of the day, though, I came up with an expression that we use to actually calculate the potential as a function of space, right? And we talked about the potential then as being some property of space. Well, if I want to decompact this expression for delta v, I find out that what I'm really talking about with change of potential is the potential defined at some point x, with reference to the potential defined at some point which I'm calling p naught. Both of these are vectors, right? Both of these both of these points are vectors. Both of these represent some point in space where I'm defining my potential as a function of x, y, and z. And one is the potential at some reference point, p naught, which isn't going to change, right? I can calculate my potential anywhere in space with the first term, with v of x. But I've chosen p naught beforehand. And actually, this v of p naught is never going to change, right? No matter, as long as I have the same charge configuration, v of p naught is always going to be the same. That's something that I choose. So in the same problem, v of x can be different, but v of p naught is the same. And so if I rewrite this as the thing that I'm probably interested in calculating when I do problems, v of x, I get it then to be minus the integral of E dot ds plus v of p naught. And now I kind of am happy because whenever I used to talk about electrostatics, say in first year physics, I always said that the potential has some global offset that you're happy to fix, right? That you have the freedom to fix. And this expression here tells me that that global offset is parameterized by this v of p naught, a choice of a location and a choice of the potential at that location. Now for charge distributions with compact support, that is, charge distributions that are localized somewhere in space, and fields that are generally localized somewhere in space, electric fields, I can often take the reference point for this to be at infinity, right? So that way, if I go off to infinity, I say, well, the potential is 0 at infinity because nothing interesting is happening there. That simplifies a lot of my problems, and I will do that very frequently when I'm trying to calculate potentials. It's not always the case, but that's a convenient place to locate to define the potential to vanish. Of course, the first example I'm going to do with you right now, that isn't the case. So I have an electric field that's just going to be in the y direction. So I picture it as electric field lines that are pointing in the positive y direction, and then the other direction doesn't really matter because the field only depends on y. In this case, I can't take the potential to vanish at infinity because the field exists everywhere. There's no good place at any of the infinities, x, y, or z, to take the potential to vanish because the field has the same strength no matter where I look. And so in this case, I'm actually going to take the potential to vanish at some arbitrary point along the y-axis, which we might as well call y of 0. And so then the potential at y equals 0 is going to be 0, and that's going to be that reference point that I care about. I'm also going to take my parameterization to be any path whatsoever. So I'm going to call ds just the vector dx, dy, dz. So my infinitesimal part of my parameterization is just going to be a little bit in the x direction plus a little bit in the y direction plus a little bit in the z direction. There's no way to get more general than that when I'm talking about a parameterization. But now when I calculate v of x is equal to minus the integral of E dot ds plus v of p naught, right? I can say, well, I defined the potential to be 0 at x equals 0. And so when I look at this integral, as long as I'm integrating from y equals 0 to whatever point it is that I'm interested in, let me still call it x vector for now, of E dot ds, I can then throw away this second part because at y equals 0, the place where I'm starting my integral, the potential energy is 0. Now my E dot ds is actually pretty easy because E only has one component, and so I have the integral from y equals 0 of E dot ds, so E is E naught y hat. But if I try to dot E naught y hat with this thing I have on the right hand side, y hat dot x hat is 0, y hat dot z hat is 0, and so the only term that remains is going to be E naught times dy times y hat dot y hat, which is of course 1. And since the only differential that remains is dy, then I know that the integral that I'm doing is only going to depend on y, and so I can replace the upper limit of integration with y instead of the full vector x. Now I'm almost done because now I have the integral of E naught dy times 1, so which is just the E naught dy. Well, the integral of dy from y equals 0 to y is just y, and so I'm left with minus E naught y. And that's still a function of vector x, right? But the only thing that matters is y. And you love this because when you look at the physics of the example, the electric field only depends on, or the electric field is constant in the y direction, right? And so moving around in x and z shouldn't have an effect on anything. And in fact, when I look at the potential function, it doesn't depend on x or z. But it is interesting to note that my potential function here does depend on y. A beautifully constant electric field in the y direction. No matter where I am in space, I should have exactly the same physical phenomena. I should have the same electric force, for example. But it turns out that when I look at the potential, because I have to define an arbitrary reference point, my potential is going to depend on where I am. It only depends on where I am in y, but it does depend on where I am. Before I go on to my next example, let me take a second and think about whether I can write down a description of the electric potential that will help me for any charge defined in a compact space. So in the last video, we derived the expression for the potential due to a point charge. We said that the potential is equal to 1 over 4 pi epsilon naught q over r, where of course this expression took into account the fact that I defined the potential to vanish at r goes to infinity. Now, if I think about calculating the potential for a single object, I have one of these expressions. But if I have many objects, then my potential is going to be given by the sum over all of my objects of the charge of that object divided by the radius, the distance to that object. And now our experience with expressions that involve sums tells us that as I allow my qi, all of my charges, to go to a continuous charge distribution, and so I'm going to replace my qi's with dq, then I can also replace my ri with that vector. So in this case, I'm just talking about the magnitude of the vector, but I know that the idea behind that r is the vector that points from my charge to my reference point. And so I can replace that with the idea of going from dq to my reference point. And I can promote this sum then to an integral over dq divided by r, where this r is the magnitude of the vector r that we've been using up to this point. And since I have this beautiful expression now, it encodes what the potential should be due to any of the charge distributions that we've been looking at, one-dimensional, two-dimensional, or three-dimensional, so long as I remember that I'm setting the potential at infinity to be 0. Okay, so now let's do a more complicated example starting with that expression. So where I had before v is equal to the integral of E dot ds, I can replace that with an expression for integrating a charge distribution over a compact support. The charge distribution that I'm going to be looking at first is a ring of charge with charge density lambda that's lying in the xy plane. And for now, I'm going to just be interested with some point that I'm going to call x vector that's above the xy plane, but it's going to be located along the z-axis, and so its component is going to be 0, 0, z. Now, even though my integral doesn't have that r hat in it anymore, I'm just doing one integral here. That is, I'm just integrating a single component because it's a scalar. I still have to think about what that vector r is going to look like, because the thing that goes in the denominator of this integral is the magnitude of that vector r that's going to point from my charge distribution to the point that I'm interested in. And so I know by looking at the picture here that the vector r is going to be, well, from point x, y, z, it's going to be pointing in the minus x direction. So that whatever x component you have, the r vector is going to be opposite to that, minus y and z, right? So this r vector points from my charge distribution to the point that I'm interested in studying. And therefore the magnitude of the r vector, which we call r, is going to be the square root of x squared plus y squared plus z squared. And now my dq, because it's a one-dimensional charge distribution, is going to be given by my charge density by times the length of that ds, right? How long is my infinitesimal charge distribution? Well, of course, this problem naturally lends itself to thinking about polar coordinates. And so if I want to write the infinitesimal length in polar coordinates, I have to remember to encode that infinitesimal length with r, the radius of my circle, and d theta, the angular variable that I need to go around the circle. Right? I can't just call it d theta because theta doesn't have any units, right? And I know that my charge density is a charge per unit length, and so that reminds me that I have to think about angular distances encoding that information that includes r. And now I'm ready to plug everything in. So I have 1 over 4 pi epsilon naught times the integral. Now I have to think about, I'm going around the circle in theta, so I go from theta equals 0 to 2 pi. Of, let's see, I have, the numerator has dq, which is a lambda r d theta, and the denominator has the square root of x squared plus y squared, let me write that correctly, y squared plus z squared. And when you first look at this expression, you start to panic a little bit because I've jumbled all of my coordinate systems together, right? I'm integrating over theta because that's the natural thing to integrate for a problem with the symmetries that I have here. But I've written down my r vector in terms of x and y, right? So this integral looks a lot more complicated than it has to be. But I can simplify it, of course, by taking x and y and rewriting them in polar coordinates, right? So x is equal to r cosine theta, and y is equal to r sine theta. And when I do this substitution, I get an integral that's a heck of a lot easier to solve, right? So in fact, what I'm going to do is I'm going to, I'm just going to pull out the two constants on the top. So I have a lambda r over 4 pi epsilon naught times the integral from 0 to 2 pi. And now all I have left in the numerator is a d theta. And in the denominator, I have x squared plus y squared, which is r squared cosine squared theta, plus r squared sine squared theta. Well, cosine squared plus sine squared is 1, and my denominator is just r squared plus z squared. Now, I probably could have seen that if I had stared at this problem long enough, right? And then I could see that the distance from my reference point to any point along my ring is going to be given by just the hypotenuse of the right triangle that's defined at that particular point. But I didn't want to jump to that because I can get it by carefully going through the steps that we've outlined. But my integral at the end of the day turns out to be now an integral over d theta where the denominator doesn't depend on theta at all. And so the only integral that I have to do for this example is the integral from 0 to 2 pi of d theta, which is of course just 2 pi. And so I'm left with a nice expression that the potential is equal to 1 over 4 pi epsilon naught times 2 pi r lambda over the square root of r squared plus z squared. And we've experienced one interesting thing that often happens in electrostatics, and that is I've ended up with an expression that depends on z. It depends on how far away I am from z equals 0. But I never did an integral over z, right? Because z was encoded in the point that I'm interested in, and my integral was over my charge distribution. And so I end up with a potential that depends on z, even though I never integrated over z. And that's a really interesting point, because when I try now, which I will do in a second, when I try to take this expression for the electric potential that I've calculated and turn it back into the electric field, that z is going to turn out to be very important, even though it kind of came along for the ride in this example as a spectator, and I didn't have to do any hard integrals with it. Okay, so in order to do this unpacking, in order to take my potential and turn it back into an electric field, I have to remind myself of the gradient operator, which is of course just the vector of all the partial derivatives, which we write sometimes as an ordered triplet, dx, dy, d by dx, d by dy, d by dz, and sometimes in component form. But I notice that if I take this operator, and I'm actually also multiplying it by -1 just because I know what's going to happen, if I take my expression for the potential and I apply the gradient operator to it, I end up first having a complicated term involving the gradient of an integral, and then I have a term that's the gradient of a constant, right? So that automatically goes to 0. This integral looks imposing until I remember that my dot product makes it easy, because ds in general is dx, dy, dz, and therefore if I write out my dot product, the first term only has x's in it, the second term only has y's, and the third term only has z's. And therefore, the only important term for the x component of the gradient of the potential is going to have all the x's in it. And so I end up with just the partial derivative with respect to x of the integral from x naught to x of ex dx, and there can't be anything simpler than that, because I just applied the fundamental theorem of calculus and I get back out the x component of the electric field. And so I see very quickly that that minus the gradient of the potential is the way to unpack all of the information in the potential and get back the electric field. Right? I've always known that integrals and derivatives undo each other, but when I have this line integral, when I have an integral over a parameterization, I can only get back out the thing that I integrated if I take the gradient of that function. So let me go back to this example of the ring of charge. I came to an expression for the potential due to this ring of charge that had some pi's and r's and lambdas in it. But remember, the only thing that it really depended on was z. Right? It wasn't one of the things that I integrated over, but it turns out to be the thing that the potential depends on. So when I want to find the electric field associated with this potential, then all I have to do is take minus the gradient of this potential. I see that the first term is going to vanish because it doesn't depend on x. The second term is going to vanish because it doesn't depend on y. And so I just have to take the partial derivative of this with respect to z. Okay? And when I do that, I end up with the electric field is equal to r lambda z over 2 epsilon naught r squared plus z squared to the 3/2 z hat. Now I could have gotten this directly from the integral expression for the electric field, but then I would have had 6 different integrals at one point to do before I found out that a lot of the terms canceled, etc., etc. Here, by going through the electric potential and doing an integral for just a scalar field, and then taking the gradient of that scalar field to get the electric field, I end up with an expression that actually wasn't so bad, right? Taking derivatives are always easier than doing integrals. And so even though I'm taking the derivative of z, where z is a z squared in a denominator of a square root, my electric field turns out to not be so bad. So I want to leave just by thinking a little bit about the relationship between the electric field and the potential. The electric field was a really intuitive object for us because it really relates to the forces that I see on test charges. But calculating the electric field from a charge distribution turns out to be really hard because it's a vector field and there's a lot going on. The electric potential, on the other hand, is a mathematical tool, right? It's something that I'm using to describe what's going on, but I can't go right from the potential to a force. The electric potential was quick to calculate because it's a scalar, but of course I can always reconstruct the electric field from the electric potential. In statics, what this means is that the electric potential encodes all of the information that was actually contained in the electric field. And so somehow the electric field, even though it has three components as a vector field, perhaps is overkill for a lot of problems in electrostatics, because I can represent all of that information in terms of just one number at every point in space and time rather than three.